Hey guys, this is part 2 of a video for my latest project. If you haven't seen part 1, take a look. Otherwise, it continues now. Alright, so let me explain really quick before we go into the results. Down here on the y-axis, we'll call it, we have the name of each of the data sets. And also, if you're wondering why it says one hot, that means I encoded the categorical features using one hot encoding. And then along the top, we have the different classifiers. So we have the base classifier, which is your baseline KNN, and then we have FASPR 1 through 6 in different variations. If you're wondering what FASPR is, I've been singing the praises of Zhao and Yu. It is their algorithm which takes into account perturbing on feature subsets, and then also using bagging and perturbing on the distance metric. They do all three. And their algorithm, which performs all three and has been shown to do well, is called FASPR. And so this column here, FASPR 1, is the FASPR algorithm implemented with the first voting mechanism. So I just did one. I didn't write the name of each of the voting mechanisms because the columns would be too big. And then the next column, FASPR 1 underscore Ks, means FASPR 1 with the same voting mechanism, but this time we also perturbed on the K value. And then it just goes all the way across. And as you'll see, there's FASPR 1 through 6 because I've implemented 6 different possible voting mechanisms. So the goal here is to find out a couple things, and we'll jump into it. Okay, other thing. I know I'm throwing a lot at you. So what do these colors mean? Blue means, so this top row, this is the anneal data set. Blue means that the smallest error was achieved by that classifier. So for this top row data set, the base classifier achieved the smallest error. Green means that when you perform a pairwise t-test, those data sets had similar performance, and red means that when you perform a pairwise t-test, those classifiers perform statistically worse, with an alpha value of 1%. So what you want is to see a classifier that has a lot of green and a lot of blue, because that means that classifier is performing the best or statistically equivalently to the best on a lot of data sets. And if we look at this big ass table, which I apologize, the font is so small, what do we find? Well, I made it easy. I put the totals at the bottom. We find that FASPR 5, so FASPR with the 5th voting mechanism I implemented, performs the best or equivalent to the best on 14 of the 20 data sets. That is really good. That blows the baseline, just normal out of the box k-nearest neighbors classifier out of the water. And in case you're wondering, yes, the hyperparameters for all of these classifiers are the same, except the ones that I explained are different. And if you're wondering, what does FASPR 5 actually mean? Because that's really more of like a code word at this point. That's when you do majority voting on the board accounts returned for the nearest K of each subclassifier. So each of your subclassifiers returns their nearest K points. Each of your subclassifiers has done a board account on them. So subclassifier 1 returns the nearest K points, and let's say you have two this is a binary classification problem. It returns the nearest K points, and the point closest, I already explained board count, you get it. Alright, so it does a board account. Each subclassifier returns the nearest K points on which your board account has already been done, and then you sum all of those results to basically determine your overall voting, and then the majority, the class that has the most votes, wins. This is awesome. This takes the benefit of a board account and the benefit of returning the k-nearest points instead of throwing them all away, and it makes a lot of intuitive sense to me why this would be a good option. There's a couple other things I want you to notice here really quick. If you just look across the bottom, you'll notice that when you perturb on the K value, so when you have this underscore KS, it's usually a good thing. So FASPR 1 classifies 6 datasets as the best. or it's the best classifier for 6 data sets. But when you have FASPR1 Ks, it classifies 8. When you have FASPR2, 9. FASPR2 Ks, 10. FASPR3, 6. FASPR3 KS, it's the best classifier. It's classifier 8 times. So if you actually look, perturbing on the K value gives you a better classifier in every single, for all of these, except, ironically, except for FASPR5. So in all other voting under all other voting mechanisms, etc., perturbing on the K value is beneficial, but for FASPR5, for whatever reason, it actually wasn't. All right. So that previous table showed us the error. Now let's get into error reduction. So this is exactly what it sounds like, the percent reduction in error compared to the baseline classifier. So you want to see high positive numbers here, and I've thrown in a blue arrow there. We can see that for the FASPR5 algorithm, our seemingly best performing algorithm, it achieves the highest error reduction. The error when you use FASPR5 is 9.9% less than the base classifier. It's a little underwhelming. You know, it's nice to know that there's a better option out there, but we're talking about fancy shit. If you only get a 9.9% error reduction, maybe that's good, but maybe that's not so good. What can we do to fix this? What can we do to get even better results, I should say? Well, we haven't tuned the hyperparameters. As I said before, all these classifiers have the same set of hyperparameters, which may or may not be optimal. So what happens when we actually tune the hyperparameters? And we'll do a quick comparison here. Basically, we have FASPR5 underscore RSCV. That means that we use the, what does that stand for? Random subset cross verification? No, sorry, random search cross validation. So basically, same type of chart as before, but this time we have tuned a few, not even all, a few of the hyperparameters. And what's the result that we get? Our newest algorithm, FASPR5 with tuned hyperparameters, is the best or equivalent to the best on all 20 out of 20 data sets. We're blowing the baseline out of the water. We're blowing FASPR5 out of the water. This is excellent. And look. I said the best or equivalent to the best. It is the best in 17 out of the 20. Only for 3 is it equivalent to the best. So this is pretty awesome. It just goes to show that if you weren't convinced by those previous, if you weren't convinced of the value by the previous figures, that there is a lot of value here, and it's hiding in the fact that you can still tune these parameters, hyperparameters, and really jack up the classifier. Let's look at the error reduction. We've improved the error reduction from 9.9% to 23%. All right, now we're talking. This is 23% tuning some of the hyperparameters, not even tuning the most important ones, like ensemble size for one. This is using random search cross-validation, which if you look that up, it's actually a very cool process. If you look it up, you let it run for a set number of iterations. How many iterations do we let this algorithm run when tuning our hyperparameters? 10. Not even that many. 10. So we've achieved a massive improvement, and there's an even greater potential improvement that you could achieve, but I didn't want to let my computer run a lot because I'm running this on 20 data sets, so I cut it off here. Yeah, but percentage-wise, 233% improvement in error reduction. That is awesome. We have basically shown that the FASPR algorithm, as described by Zhao and Yu, who are total homies, I love your work, it was actually delightful to read, is great. And to take a little bit of credit away from them really quick, though, their algorithm is great, but also the dank voting mechanisms that I implemented are also great, because remember, this isn't just plain old FASPR. This is FASPR with some sick voting incorporated in it. All right, so what are the conclusions we have here? 1, you can create an effective KNN ensemble. Awesome. FASPR5, as I called it, I already explained what that is. Not gonna say it all again. is excellent. Perturbing on the k-values can be beneficial, depending on your other hyperparameters and specifically your voting mechanism we've seen, but it can often be beneficial. And the final thing that we learned, which I am not going to talk about in this video, I'll briefly explain it, is that VDM encoding is better than one-hot encoding. I explained earlier that for each of my 20 data sets, categorical features were encoded using one-hot encoding. VDM encoding is better. So it was actually, you won't be surprised, proposed by Zhao and Yu, but basically VDM encoding is it's just a more intelligent way of encoding categorical data, which I'll leave it at that. But it's a way that provides more information such that all right, I'll try to give you a simple example to explain it. Imagine you have a data set and you have a categorical variable dog and cat. And your set of data where this one particular feature, where your pet feature says cat, and your set of data where your pet feature says dog, let's say all other features in those two data sets are equal except the pet feature, cat and dog. Well, in that case, that pet feature, doesn't really provide any extra information. Because, sure, the feature itself is different, but all other features are the same, and the classifications for both of those data sets are the same. So that pet feature tells you nothing. And when you use one-hot encoding, that pet feature, even though it tells you nothing because it's effectively the same, will be encoded as different. Dogs and cats are different. With the VDM encoding, it will look at that pet feature, it'll see like, oh look, this feature is literally the same, it just says a different thing, it provides no new information to discriminate between the classes, and it will encode those features similarly. And it's done in a very nice way where it encodes directly to a value, and then you can apply Minkowski distance, blah, blah, and it's all good. So, I have spilled a lot of words. I am not a concise individual. I need to improve this. But, yeah, if you're interested in this project, I'm putting the links in the description down below. I'm really happy with this because, honestly, it's the first time I've taken some academic papers, and unless you think I'm fucking around, I got a whole lot of them. I've read all of these, I've annotated all of these, I understand most of them pretty well. And it's the first time that I've, reproduced someone's work. This particular problem with the KNN Ensemble was something that would have helped me for a project I was working on a year ago a lot. So, I feel my own feelings of accomplishment for producing it. And I'm putting it out there so that anyone else can play around with it. And I don't know if anyone will, but it's out there. And the link is in the description. So, hope I didn't talk your ear off, and have a good day. Oh, one other thing. My references, because always say your sources. Alright, that's it. Bye.